Welcome to the third video of limits involving infinity. Today we'll discuss vertical asymptotes. We've already talked about horizontal asymptotes, which is the end behavior of a function, what happens on both the right and left ends. And today we'll be talking about the other type of asymptote, which is a vertical one. The probably simplest graph to take a look at is the rational function f of x equals 1 over x. This is the parent rational function, the simplest type, x being in the denominator. So we can clearly see that our domain is all real numbers except 0, since plugging in 0 would be 1 divided by 0 or undefined. And if we take a look at our function, when x is 0, which is the vertical line, also known as the y-axis, we can see that our function never quite hits it. If we sort of get closer to our graph, if we take a look at what happens just to the right of when x is 0 here, the y-axis, we can get really close, but we can see as we go even, infinitely north here, going up, our graph never quite touches there. It does look like it does if we zoom out. Then if we look at to the right of the y-axis, the vertical line x equals 0, and we see that our graph is going down towards negative infinity, again, never quite touching the line x equals 0 or the y-axis, but getting infinitely more negative as we approach x equals 0 from the left-hand side. And so we say that the line x equals 0, that vertical line here, is a vertical asymptote because on either side of it, our function is approaching either negative or positive infinity. All right, I have messed with the graph a little bit, and this is now the graph of 1 over x shifted 3 units to the right. We have a horizontal translation here, and we can see that it's the exact same shape of the graph, these two curves, but now instead of our vertical asymptote being x equals 0, it's now x equals 3. Notice the pattern. The value that is no longer in our domain is now 3, since if we plugged in 3, we'd have 0 in our denominator. So this time our domain is all numbers except 3. Therefore, plugging in 3 would make our denominator 0. Nothing cancels top to bottom. And so 3 is the issue here. I didn't draw this in before, but I can sketch in the vertical asymptote with a dotted line to show that it is in fact a vertical asymptote. And we can see that clearly on either side of our function here, either side of when x is 3, we can see that our graph, and that's not going to stay still, but that's okay. We can see that our graph is approaching positive infinity as we approach from the right-hand side, and our graph approaches negative infinity when we approach from the left-hand side. And so that is the definition of a vertical asymptote. A vertical asymptote's any vertical line when the graph approaches either positive or negative infinity on either side of it. We can explore what those vertical asymptotes are by, if necessary, factoring the denominator and seeing what makes the denominator 0 when nothing cancels out. So in this case, the value that makes our denominator 0 is 3. There's no x minus 3 that cancels, once we factored or anything. This one doesn't need factoring because it's so simple, but there's no canceling here. 3 makes the denominator 0 without any sort of canceling top to bottom. Therefore, the line x equals 3 is our vertical asymptote. Just like before when we had 1 over x, the line x equals 0 was a vertical asymptote for that one because 0 made the denominator 0 and nothing canceled top to bottom. Let's explore the definition of a vertical asymptote using mathematical words and notation. Okay, here is the definition officially of a vertical asymptote. This comes right from your book on page 72. And we have the line x equals a, which is a vertical line. That line is a vertical asymptote of our function if we approach a from the right or the left, our function goes to one of the infinities. And we saw that that was the case in our previous two examples. So be sure that you get this written down. Again, this is a limit involving infinity, but instead of infinity being down here, such as in the horizontal asymptotes, The infinities are over here. Now we can say that a one-sided limit, either a right or left, goes to infinity or negative infinity. We would not say an overall limit goes to infinity or negative infinity. We would say that the overall limit does not exist, but it is completely mathematically fine if we say that either a right or left-sided limit goes to positive or negative infinity. Let's explore one of the most common graphs that has a ton of vertical asymptotes, actually an infinite amount. Let's explore the graph of the tangent of x. So let's let f of x be tangent of x, and I brought our unit circle here just to be our little guide. And I know that we went over the unit circle at the start of the year. I want us to continue working with trig because it is such a big part of calc. It's super integrated into calculus as we move forward. So I don't want us to forget what tangent is. Let's do a quick reminder of what tangent is. Tangent, you can look at tangent as either sine over cosine, which is what it is by definition. And then remember that the sine is the y-coordinate and cosine is the x-coordinate. So in a more simplistic way, the tangent is the y-coordinate divided by the x-coordinate. And in math, whenever we have a fraction, we always have the possibility to have undefined values when the denominator is 0. So as we go around our circle and find the tangent at different spots, if x is ever 0, we're going to write that the tangent, f of x, is undefined. So let's look at the tangent at a few different locations to explore what the vertical asymptotes are. All right, let's look at the tangent at the main 5 locations here. So 0, pi over 2, pi, 3 pi over 2, and back to 2 pi. All right, let's start at the tangent of 0. The y-coordinate is 0, and the x-coordinate is 1, and 0 over 1, so I'll write this all out, 0 over 1 is in fact 0 simplified. All right. Let's find the tangent at pi over 2. So we're plugging in pi over 2 here into our function. Here's pi over 2. The y-coordinate is 1, and the x-coordinate is 0. And so we'll have 1 over 0, which is undefined. All right, I'm going to do the same thing for these 3 other spots here. All right, so I filled in the other 3 spots. Again, you don't have to write this first thing. I just wanted to show our thought process. This is like our final answers here. And so when we graph this, I'm going to need a few more spots as well. So let's just start by graphing these 3 zeros. We can't really graph in undefined yet. Okay, so this is special trigonometric coordinate graph paper that I found, so I'm able to easily graph it. So we have the coordinate point 0, 0. We have pi, comma 0, and we have 2 pi, comma 0. Then the undefines, I said we can't really graph, but the undefines are when the denominator is 0, nothing cancels it out. So these values are actually our vertical asymptotes since they make our denominator 0 and nothing cancels. So we can actually graph these as the vertical asymptotes. So there is a vertical asymptote at pi over 2 and at 3 pi over 2, since that's where the tangent is undefined. All right, now I want us to also explore the negative radians, the negative parts of our unit circle. What does negative mean? Let me first write them over here. So I want to explore negative pi over 2 down to negative 2 pi. What does it mean to be negative on the unit circle? It means just go the other way. So this is the normal way around the unit circle, like traveling to here is positive pi over 2. If we traveled negative pi over 2, I'm going that same distance, a quarter of the way around the unit circle, 90 degrees, except I'm going in the negative direction. So negative pi over 2 is actually the same spot as positive 3 pi over 2. It's like going a quarter this way is the same as going 3/4 the other way, right? So going a quarter this way is the same as going 3/4 this way. Didn't mean to just confuse you more if that's what that did. Anyway, so negative pi over 2 is down here. So finding the tangent down here, it's just negative 1 over 0, which is undefined. And then negative pi is halfway around. Negative pi is the same as positive pi, because we just went halfway either way. So the tangent here is 0. It's 0 over negative 1. The tangent at negative 3 pi over 2 is undefined. And negative 2 pi is going all the way around back to where we started. It's the same as 0 or positive 2 pi. So the tangent here is 0. So let's graph those other points. So we have the coordinate points negative pi, comma 0, and negative 2 pi, comma 0. We're undefined at negative pi over 2 and negative 3 pi over 2. Therefore, we have vertical asymptotes there. But what happens in between? I need to know what our graph looks like here, 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 just to see what tangent looks like. Well, what's halfway between 0 and pi over 2? What's halfway between 0 and pi over 2, between 0 and 90 degrees, right, is halfway, 45 degrees, or pi over 4, right? Halfway between 0 and a half a pi is a quarter of a pi. And so in order to find what the tangent is there, we take the y-coordinate over the x-coordinate. I'm not even going to write that out. The y-coordinate and the x-coordinate are the same number. What is anything divided by itself? 1. So when the tangent of pi over 4 is 1, because root 2 over 2 divided by itself is 1. Let's take a look at the next spot between pi over 2 and pi, right here. Between pi over 2 and pi, halfway is 3 pi over 4. And again, they're the same x and y coordinate except one of them's negative. So when we find the tangent of something divided by its opposite, that's negative 1. Filling in the rest, the tangent of 5 pi over 4, we have something divided by itself again, that's 1. And the tangent at 7 pi over 4 is something divided by its opposite, negative 1. So plugging in those points, we have a couple more points here. I need to find the negative versions of those as well. Okay, I need to find the tangent of negative pi over 4. So going in the positive direction, pi over 4 is here. I went halfway through a quadrant. Going negative pi over 4 is down here. I went the opposite way the same distance. The tangent here is something divided by its opposite, therefore it's negative 1. Going around the unit circle, we see that it's basically the same pattern, but just opposite. For the last part here, I just want to know kind of what the overall form of tangent looks like. And I already know that it looks kind of like a squiggle here and it approaches our vertical asymptotes like that. But I just want to show you how we can figure that out without using a calculator. If I wanted to find maybe one more point here, something between pi over 4 and pi over 2, I can use the unit circle. What's between pi over 4 and pi over 2? Pi over 3. So I'm going to find the tangent of pi over 3. And the tangent of pi over 3 would be its y value divided by its x value. And when we have a complex fraction like that and something's the same, like the denominators, we end up just getting root 3 over 1, which is root 3. And root 3 is about 1.7. It's close, 1.72, I think, or 3, something like that. So I know that it's approximately 1.7. So we can graph that. And something just like that. The idea is that if you were to find a few more spots, you'll see that this is the general shape of tangent, and it repeats and repeats forever because you can continuously go around the unit circle infinite times. Every time that you hit pi over 2 or 3 pi over 2, here or here, your tangent is undefined. And we can see that because it's a vertical asymptote every time there's a pi over 2 or a 3 pi over 2. So let's define this. Let's focus on this vertical asymptote at pi over 2. We would say that the limit as x approaches pi over 2 from the right of our function f of x, as we're approaching pi over 2 from the right, our function approaches negative infinity. As we approach pi over 2 from the left, here's pi over 2, as we approach it from the left side, our function approaches positive infinity. which you can put a plus sign in front of the infinity, but you don't need to. Now, because pi over 2 is not the only vertical asymptote, there are infinitely many, and this goes on, we can kind of say a pattern. So instead of writing pi over 2 every single time, I'm going to just call this A. And let's think about what A is, because this happens every single time. How can we define A? Well, A is every time we have pi over 2, 3 pi over 2, and the next one will be 5 pi over 2, 7 pi over 2, same thing in the negative direction. So it's all the odd multiple of pi over 2. The way that we can write that is these limits approach negative and positive infinity if A is an odd multiple of pi over 2. And I erased what f of x was, which is important. Number f of x was the tangent of x. That is what we've been focusing on. So tangent is a very important trigonometric function because it is sine divided by cosine by definition. It has an infinite amount of vertical asymptotes every time we hit an odd multiple of pi over 2. We're going to end the video with 2 quick examples of finding vertical asymptotes in other graphs, not trigonometric graphs, but just rational functions. So I'm going to take a look at Desmos and then also figure out how we can do this algebraically without Desmos. So for this function here, this rational function, we want to find the vertical asymptotes, then describe the behavior to the left and the right of each one of those vertical asymptotes by using limit notation. Can you guess where we would have issues here? Think about the values that would make this denominator 0. If you said 2 and negative 2, you're absolutely right. You can just think about that algebraically, right? What do you plug in for x that makes this denominator 0? You could have factored this, since it's a difference of squares, x plus 2, x minus 2. No factors cancel top to bottom, so the issues are negative 2 here and positive 2 here that make them 0 in the denominator. But if we just take a look at the graph, we can clearly see that our function here, we have a vertical asymptote at x equals negative 2, and we have another vertical asymptote as x equals positive 2. Our graph approaches negative and positive infinities on either side of each one of those vertical lines. So algebraically, we found that what makes each of these factors in the denominator 0, right, that nothing cancels in the numerator, the vertical asymptotes are the lines x equals negative 2 and x equals positive 2. So we did the first part. Now let's describe the behavior to the left and the right of each one of those. This is best done by just looking at your graph. Let's first take a look at the vertical asymptote x equals negative 2, which is this vertical line. As we approach negative 2 from the right, our graph approaches negative infinity, and as we approach negative 2 from the left, our graph approaches positive infinity. So we would write and describe the behavior just like this. If we take a look at the other line, x equals 2, which is dotted in pink, we can see that as we approach 2 from the right, our graph is shooting upwards towards positive infinity, and as we approach 2 from the left side, our graph is shooting down towards negative infinity. This last function is again a rational function, and I'm going to factor the denominator. When I factor that, I'll do that in pink. When we take a look at this denominator, this is a quadratic trinomial. It's a little more difficult to factor than the previous example. A is 2, it's not 1. So I'm going to need to find 2 numbers that multiply to negative 6 that add to negative 5. So 2 numbers that multiply to negative 6 that add to negative 5. And those numbers are negative 6 and positive 1. So then we'll write it out. We'll have 2x squared minus 6x plus 1x minus 3. So I just replace negative 5x with these 2 values. Then we'll factor by grouping, which I'll do in green. We can take a 2x out of here, and we're left with x minus 3. Then this group I'll do in blue. I can just take a 1 out, and we're left with x minus 3 again. Our final answer is the stuff on the outside and then the stuff on the inside. So we can rewrite this function as 1 minus x, which I'm going to rewrite as negative x minus 1, so it looks like a factor in the numerator, over 2x plus 1 times x minus 3. I did this in the numerator to see if x minus 1 would cancel with anything, and it didn't. Oops. So the values that make each one of these 0 down here, this one's easy to look at and see that x equals 3 would be a vertical asymptote. Since 3 makes this factor 0, you can take a look at this and see that negative 1/2 would make this factor 0. And if you need to do that off to the side, just set it equal to 0 and then solve. And you'll get negative 1/2. So our vertical asymptotes are going to be the vertical lines x equals negative 1/2 and x equals 3, and we did that algebraically. Let's take a look at the graph on Desmos to just make sure. All right, we can see on our graph that the line x equals negative 1/2, a little harder to see on here, is a vertical asymptote. So is the line x equals 3. Let's take a look at x equals negative 1/2. We want to describe the behavior to the left and the right. It's hard to write this fraction very small. So the behavior to the right of negative 1/2, so here's negative 1/2. To the right of it, our graph is going down towards negative infinity. And our limit, our left-sided limit, the behavior to the left of that vertical asymptote, our graph is going towards positive infinity. Go ahead and try the left and the right limits for the vertical asymptote x equals 3 next. All right, our two limits. As x approaches 3 from the right, our graph is going down towards negative infinity, and as x approaches the vertical asymptote x equals 3 from the left, our graph is approaching positive infinity. And therefore, those are both our vertical asymptotes. So now we know how to factor and find those vertical asymptotes algebraically. We also can look at our graphing calculator and find them graphically, especially seeing what the behavior is to the right and to the left of each one of those vertical asymptotes. So thank you for bearing with me through this slightly longer than usual video, but you only had one today, so it's not too bad. And hopefully now you understand vertical asymptotes, how to find them both algebraically, graphically, and find the behavior to the right and to the left using right and left-sided limits.